So far, our treatment of digital circuits has been on the more mathematical side, treating things very ideally. What I want to talk about next is some of the practical considerations you run into when actually building digital circuits. So the first is that we draw these circuits as these symbols with inputs and outputs, and we say, okay, there's this much voltage at this one and this much voltage at this one, and that the logic of the AND gate or whatever determines if the output is on or off. But we're glossing over the fact that these are, wires with voltages and therefore have currents going into or out of them. So our gates at the inputs can have current flowing into them or out of them depending on what's going on. So there can potentially be current flowing in or out of the inputs. And we can also have current flowing in or out of the outputs. So if we do something like have a, let's say we have an inverter, a NOT gate connected as the input to our AND gate. So if we have this at 0 volts, that means the inverted value here is going to be 5 volts. To keep this at 5 volts, we are going to have current flowing into this gate, and that is going to have to be coming from this gate, from the power supply. So, there's an implicit plus 5 volt power supply connected to this, and that's going to have to be supplying current through the gate into this next one. To keep this at 0 volts, it is often the case that we will have to have current flowing out of this, going, this, whatever is making this to be at 0 volts has to sink some amount of current. Anyway, the point is we're not going to worry about you analyzing circuits like this, but I just want you to be aware that these sorts of things happen in these logic gates, and that's something we have to worry about. So gates are limited in the amount of current they can source and sink at the output, and the amount of current they need at the input in order to keep the input what it's supposed to be, 0 or 5 volts. This leads to the idea of, the connection between these is something called fan out. And the idea of fan out is maybe this output of this gate, I want to do multiple things with it elsewhere in the circuit. So the fan out of the gate is the number of gates that I can have this as the input to and still not ask too much current of this. So this is basically the number of inputs that you can drive from a single output. And it's called fan out because maybe, schematically that would look like this, right? All of these are, these are all inputs to some other gates. And each of these needs some amount of current that has to be supplied by this. And so the fan out is kind of a shorthand for the ratio of how much current this can supply to how much current each one of these needs. Okay, so in other words, for TTL, typically, or maybe I should say ideally, there are some, I think, you generally do things that decrease this number rather than increase this number. The fan out for TTL is roughly 10. So that means I can drive 10 gate inputs with the output of a single TTL gate. If I try to do more than that, I'm going to be drawing too much current from this, and I'm going to not get the behavior I want. For CMOS gates, because these are a different kind of transistor and they draw so little current at the inputs, for CMOS it is thousands. You can drive thousands of gates with a single gate output. Of course, you do run into problems. Usually those tend to be related to like how fast you want things to switch or the capacitance of the system or things like that. So, but anyway, with CMOS, this is much less of a problem because so much less current is drawn. Anyway, I don't want you guys to worry too much about this. This is a practical thing. If you're building circuits, knowing how much current is going into your logic gates and coming out of your logic gates when they are on or off is something to pay attention to. And as for many other things, Horowitz and Hill is a good source for the details of all of this. Okay, so next I wanted to talk about resistors, circling around back to chapter 1. So what we're going to talk about now is what are called pull-up and pull-down resistors. So to illustrate the idea of pull-up and pull-down resistors, we'll start with an example. So let's say I have a logic gate that I want to drive, and we'll just make this an inverter to keep this very simple. So here's my inverter. This is my NOT gate, and I have an input over here and an output over here. And maybe this is part of a logic circuit in some machine with switches that I'm flipping, and so those switches are connecting and disconnecting wires that I want to be used to control other parts of the circuit. So in other words, I'm using those switches as logical inputs to some logic. In this case, it's just a NOT gate, but we could do some very, very complicated thing if we wanted to. Okay, so let's say I have something like this. I want a switch where if I close the switch, it makes the input 0. If I open the switch, it makes the input plus 5 volts. So maybe I could do it with something like this. So I put the switch here and connect this end of the switch to ground. Okay, so this is simple enough. I know that when the switch is open, I want it connected to 5 volts. So maybe I can just do something like connect plus 5 volts here, and maybe that will work. I'm gonna put a question mark next to this because this is a hypothetical circuit that we're going to see is not ideal. So would something like this work? So if the switch is open, 5 volts is connected to the input, which is what we want, so the output is going to be 0. That makes sense, that works. If I close this switch, now I have a wire connecting the input to ground, but I also have a wire connecting the input to plus 5 volts. So 1, which of those is going to win? And 2, that's actually a big problem because we've now also connected our plus 5 volts directly to ground, which is going to cause it's going to cause that to not be plus 5 volts anymore, and there's going to be a large amount of current flowing down. So that's a problem. So the way around this is with what's called a pull-up resistor. So this here is my pull-up resistor. So what this is doing is when nothing else is connected, when this switch is open, this resistor is acting to pull this input up to 5 volts, right? Very little current is drawn by the NOT gate, so there's going to be very little current through this resistor, and so there's going to be a small voltage drop across it. So here, this is going to be close to 5 volts, maybe 4.9 volts, maybe 4.8 volts. It doesn't matter because for these sorts of circuits, anything above 3 volts or look at your spec sheet is perfectly fine for telling the logic gate that it's a on signal. However, even though this resistor is connecting this to plus 5 volts, when I close this switch, now I have something that looks like this, plus 5 volts connected to my input, connected directly to ground. Oops, sorry, no I don't. I have a resistor here now. So I have a resistor here now, so I'm connecting my input directly to ground. This is like continuous wire, and there's this resistor to 5 volts. So there will be a 5 volt drop across here. There will be some amount of current flowing through that resistor, but that is not going to change what this input is feeling. This input is going to feel 0 volts for sure when the switch is closed. So So this is good. This is doing a couple things. This is removing the ambiguity of what's happening when this switch opens and closes, and it's also limiting the amount of current that is flowing from plus 5 volts to ground when this switch is closed. So for TTL circuits, for the currents and voltages that are commonly used, typical values might be 1 to 5 K resistors. And so, if you have a resistance that's too much lower than that, you're going to be flowing more current than you need and dissipating more power. And if it's too high, it might not be enough to keep this input near 5 volts when the switch is open. All right, cool. You can also do the opposite, so that's a pull down resistor. So instead, if you wanted the switch to connect your plus 5 volts to the input, you could also have something like this. So here our switch is connecting plus 5 volts to the gate. And now if the switch is closed, this is plus 5 volts. If the switch is open, like what's happening here? Nothing is happening. Nothing is connected to this, right? That's definitely ambiguous in how the logic gate would respond to that. So a pull down resistor would be connected between there and ground. And so when this switch is open, we have our input resistor, ground. Because there's not very much current flowing, this is going to be pretty close to ground still, within some tenths of a volt. And so that will still be a logical off signal. And when this is closed, plus 5 volts is connected directly to the input. So yeah, pull up and pull down resistors. You see these very often in circuits with digital logic.